Look at your hand. The atoms in it, like carbon, oxygen, nitrogen, and iron, are, by the universe's own accounting, a curiosity, a rare exception. Everything you have ever seen, touched, or measured makes up approximately 5% of what the universe actually contains. The remaining 95% has never been directly detected by any instrument ever built. It fills the space between galaxies, holds every star cluster together, and is quietly accelerating the expansion of everything you will ever see. Tonight, you are going to travel into the structure of what we know, and into the far larger structure of what we don't, and understand why the universe is not made of stars. It is made of something else entirely, and we are only beginning to suspect what. Before we dive in, if you love exploring the scale of the cosmos as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now, let's begin. It is almost impossible from our current vantage point to appreciate how radical the first few revisions to this picture actually were. When Nicholas Copernicus, in the middle of the 16th century, proposed that the Earth was not the center of the cosmos, but rather one of several planets orbiting the Sun, the immediate implication, the one that made the proposal genuinely disturbing to the people who understood it most deeply, was not that the Earth had been demoted. It was that the universe had gotten larger. If Earth moves around the Sun, then the stars cannot be nearby objects fixed to a sphere just above us. They must be extremely distant, so distant that Earth's movement around the Sun produces no visible shift in their apparent position. The lack of observable parallax, the ancient argument against a moving Earth, turned out to be evidence not that Earth stood still, but that the stars were incomprehensibly far away. The universe had just gotten bigger by an order of magnitude that could not yet be measured. Then, Galileo Galilei pointed his telescope skyward in 1609 and discovered something that the naked eye had entirely missed. The Milky Way was not a continuous cloud of luminous gas. It was stars, countless individual stars, packed so densely that the naked eye blended them together into a single soft glow. The universe had just gotten bigger again, not by a factor of 2 or 10, but by some factor that could not yet be specified, because no one knew how many stars were now visible or how far any of them actually were. For the next 3 centuries, the question of cosmic scale was largely the question of stellar distance. Astronomers developed increasingly sophisticated techniques for measuring how far away the nearest stars were, using the parallax method that Copernicus's critics had cited as evidence against a moving Earth, now deployed as a precision measuring tool. By the late 19th century, it was clear that even the nearest known stellar system, Alpha Centauri, lay roughly 4 light-years away, a distance so immense that the number itself requires a pause. Light travels at approximately 300,000 kilometers per second. In a single year, it covers roughly 9.5 trillion kilometers. 4 light-years is therefore about 38 trillion kilometers. The very closest individual star to our Sun, Proxima Centauri, a faint red dwarf gravitationally associated with the brighter pair Alpha Centauri A and B, and discovered only in 1915, sits at about 4.24 light-years. Every other star in the Milky Way is farther than that. Here is where the story really begins to accelerate. Because for most of the 19th century and into the early 20th, the dominant assumption among astronomers, the working model that shaped all observations and all calculations, was that the Milky Way was the universe. Our galaxy, the great swirl of hundreds of billions of stars we inhabit, was assumed to be the entirety of everything. There were objects in the sky called nebulae, soft, cloudy patches of light that didn't look like individual stars. And the debate about what they were had been ongoing for decades. Some astronomers thought they were clouds of gas within our galaxy, protostellar nurseries where new stars were being born. Others suspected they might be something more, island universes. In the phrase of the philosopher Immanuel Kant, galaxies like our own, lying at unimaginable distances. The debate was resolved, decisively and permanently, in the years 1923 and 1924. Working at the Mount Wilson Observatory in California, Edwin Hubble identified the first Cepheid variable star in the Andromeda Nebula on a photographic plate taken in October 1923, and over the following months, used additional Cepheids to measure its distance, a result he announced at the close of 1924. Cepheid variables pulse with a brightness that is directly related to their intrinsic luminosity, a relationship discovered by Henrietta Swan Leavitt in 1908, whose work made distance measurement at cosmic scales possible and whose contribution to astronomy is still not as widely known as it deserves to be. By identifying Cepheid variables in Andromeda and measuring their pulse periods, Hubble was able to calculate that Andromeda was not a gas cloud within our galaxy. It was a separate galaxy lying at a distance of roughly 900,000 light-years from Earth, a figure later revised upward to approximately 2.5 million light-years, but in either case vastly outside the boundaries of the Milky Way. The universe had not merely gotten bigger, it had exploded in scale in a single observation. Every nebula in the sky, there were thousands of catalogued ones, was potentially a separate galaxy. Each one contains hundreds of billions of stars, each one a Milky Way unto itself, lying at distances that made the already staggering stellar distances look trivial by comparison. This is the pattern we will trace throughout everything that follows. Not once, not twice, but again and again, the universe turns out to be larger than the largest estimate we had just settled on. And each expansion of scale carries with it not just a revised number, but a revised understanding of what kind of place we are living in and what our presence here means. Before we move outward through those nested shells of scale, it is worth pausing on the mechanism that makes any of this knowable at all. The universe reveals its size through light, specifically through the time it takes light to travel. When you look at the moon, you are seeing it as it was about 1.25 seconds ago. That gap is so small as to be functionally undetectable in ordinary experience. When you look at the sun, you are seeing it as it was approximately 8 minutes ago, meaning that if the sun vanished at this exact moment, you would not know for 8 minutes. The nearest star beyond our sun, Alpha Centauri, is about 4 years in our past every time we observe it. The Andromeda Galaxy, the nearest large galaxy to our own, appears in our telescopes as it was roughly 2.5 million years ago, before our species existed. Before the genus Homo existed. In fact, since the earliest fossil evidence of Homo habilis dates to roughly 2.5 million years ago. This is a remarkable and slightly vertiginous fact. When you look at Andromeda, you are seeing a time before humans. The galaxy has had 2.5 million years since that light was emitted to change in ways we cannot yet see. And Andromeda is our immediate neighbor on cosmic scales. The light reaching us from the most distant galaxies detected by our telescopes has been traveling for over 13 billion years. Those galaxies existed when the universe was less than 1 billion years old, when it was a small fraction of its current age, when the first stars were only just beginning to ignite. We are not seeing them as they are. We are seeing them as they were, in a universe so young it would be unrecognizable to us today. This point, that light travel time means we are always looking into the past, is not merely a philosophical curiosity. It is the foundational constraint that shapes everything we know and everything we cannot know about the universe's size. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is bounded not by anything physical, but by time itself. There is almost certainly more universe beyond that boundary, possibly a great deal more, but we cannot see it. Its light has not yet arrived. The observable universe, by the most current measurements, has a diameter of approximately 93 billion light-years. Hold that number for a moment. Do not try to visualize it. Visualization fails at these scales. Simply acknowledge it. The sphere of space we can, in principle, observe, the totality of everything that has ever been able to send us a signal, stretches 93 billion light-years across. And the universe it is embedded in, the whole universe, the complete extent of space, is almost certainly larger, possibly much larger. Possibly, as the physics of cosmic inflation suggests, incomprehensibly larger, possibly infinite. We will get to all of that. But we need to build the ladder carefully, one rung at a time, because the only way to genuinely understand scale in cosmology is to feel each step before taking the next one. The numbers alone, read off in sequence, produce a kind of numerical vertigo that registers as awe, but does not actually change how you understand the universe. What changes understanding is context, the mechanism behind each scale, the history of how we measured it, the human stakes of what that measurement means. So we begin where scale begins, not in space, but on the ground. The earth beneath you right now, assuming you are lying down as this format encourages, has a radius of about 6,300 kilometers. That is a number most people encounter in school and immediately forget because it does not correspond to any experience they have ever had. The Earth feels, from the surface, essentially flat in any direction you can walk. The curvature is too gradual and too large to be visible to the naked eye at ground level. But from space, from the altitude of the International Space Station, at roughly 400 kilometers above Earth's surface, the curvature becomes visible and Earth looks unmistakably like a sphere. Those 400 kilometers feel large from the ground. They feel especially large if you think about driving them on a road. 400 kilometers is roughly the distance from London to Edinburgh, or from Los Angeles to San Francisco. A comfortable 5-hour drive on a straight highway. But in terms of Earth's radius, 400 kilometers is about 6%. The International Space Station, our most continuously inhabited structure beyond the surface, orbits at a distance equivalent to less than 1/20th of Earth's own radius above the ground. It is profoundly close. The Moon, our nearest significant neighbor in space, lies at an average distance of roughly 384,000 kilometers from Earth. That is about 60 Earth radii, meaning you could stack 60 Earths in a line between the surface of our planet and the Moon. The Moon is far enough away that a beam of light takes about 1¼ seconds to reach it, and yet it is close enough that human beings have traveled there. 12 of them walked on its surface between 1969 and 1972, carried by rockets burning chemical fuel of a kind not fundamentally different from the fuel that powers a space shuttle. These numbers, Earth's radius, the distance to the Moon, are worth holding before we move further because they represent the scale at which human beings have direct physical experience. We live on Earth. We have visited the Moon. Everything beyond the Moon is, at present, beyond direct human reach, accessible only through light, through telescopes, through the mathematics of orbital mechanics and spectroscopy, and the physics of the expanding universe. And the distances beyond the Moon escalate with extraordinary speed. Mars, at its closest approach to Earth, lies roughly 55 million kilometers away, more than 140 times the distance to the Moon. At average distances, the gap is closer to 220 million kilometers. A light beam takes anywhere from 3 to 22 minutes to make the journey, depending on where the two planets are in their orbits. Human beings have sent robotic spacecraft to Mars, and those missions take between 6 and 9 months of travel time. Mars is our nearest planetary neighbor in the direction of the outer solar system. Beyond Mars lies the asteroid belt, and beyond that, Jupiter, the largest planet in our solar system, orbiting at an average distance of roughly 778 million kilometers from the Sun. The light from the Sun, traveling at the maximum speed permitted by physics, takes about 43 minutes to reach Jupiter. Saturn lies at about 1.5 billion kilometers. Uranus is nearly 3 billion. Neptune, the outermost of the 4 giant planets, orbiting at an average distance of roughly 778 million kilometers from the Sun, a distance at which the Sun appears not as the overwhelming disk we know from Earth, but as a very bright star, still enormously more luminous than any other star in the sky, but no longer a disk visible to the naked eye. The Voyager 1 spacecraft, launched in 1977, and now the most distant human-made object in the history of our species, crossed the boundary of the heliosphere, the region of space dominated by the solar wind, somewhere around 2012, at a distance of approximately 121 astronomical units from the Sun, where 1 astronomical unit is the average Earth-Sun distance of about 150 million kilometers. At that distance, the radio signals Voyager sends back to Earth, traveling at the speed of light, take over 17 hours to arrive. Voyager has been traveling continuously for more than 4 decades. It is the product of our most sophisticated rocket technology and the gravitational assistance of multiple planetary flybys. And it has covered in all that time a distance that is still only a tiny fraction of 1 light year. 1 light year, the distance light covers in a single year, is approximately 9.5 trillion kilometers. Voyager 1 travels at roughly 17 kilometers per second. At that speed, it would take over 70,000 years to reach the nearest star. The distance between stars is the first scale at which our intuitions completely fail us. Within the Milky Way, the average distance between stars is roughly 4 to 5 light years. That is the average, meaning most stars in our galaxy are separated from their nearest neighbors by distances that would take Voyager 1, traveling at its current speed, somewhere between 70,000 and 100,000 years to cross. Our galaxy contains somewhere between 200 billion and 400 billion stars. The uncertainty in that estimate alone, a range of 200 billion stars, is itself larger than most people's intuitive sense of a lot. Picture the Milky Way as a disk. It is not a perfect disk. It is warped slightly at the edges, like a vinyl record left too long in the sun. But the disk approximation is useful for building a mental map. The disk is roughly 100,000 light-years in diameter. Its thickness varies. The central bulge, a dense concentration of older stars surrounding the galactic core, is perhaps 15 to 20,000 light-years thick, while the thin disk of the spiral arms, where our solar system resides, is only about 1,000 light-years thick. Our solar system sits roughly 26,000 light-years from the galactic center, in a relatively quiet stretch of one of the outer spiral arms called the Orion Arm. This means that if a beam of light were to leave Earth right now and travel toward the center of the Milky Way, it would arrive roughly 26,000 years from now. In 26,000 years, human civilization has risen and fallen countless times in microcosm. Every recorded human history fits within that window of time. The galactic center is not distant in the way that Mars is distant, a thing separated from us by months of travel time. It is distant in the way that the emergence of agriculture is distant, separated from us by an interval longer than everything we know ourselves to have been. And yet, the galactic center is well within our own galaxy. It is local by the standards of what comes next. The Milky Way rotates. Our solar system completes one orbit around the galactic center approximately every 225 million years, a span of time called the galactic year, or cosmic year. In one galactic year, the entire history of complex animal life on Earth would fit with room to spare. Dinosaurs appeared and disappeared in less than one galactic year. The formation of the Rocky Mountains, the opening of the Atlantic Ocean, the rise and extinction of countless species, all of that happened within the most recent galactic year of Earth's existence. Our Sun has completed roughly 20 galactic orbits in its lifetime. It has been around the galaxy 20 times. This dwelling on the galactic scale is necessary because the Milky Way will shortly become the equivalent of a single grain of sand on a very long beach. But before we let it shrink to that, feel its actual enormity for a moment. 100,000 light years across, 200 to 400 billion stars. A rotating disk warped at its edges with a supermassive black hole at its center. Sagittarius, a star, with a mass approximately 4 million times that of our Sun, anchoring everything in an invisible gravitational embrace. The Milky Way is an object of staggering complexity and scale, and it is the entirety of everything that human beings called the universe until 1924. Now we move to the next shell. The Milky Way is not alone. It is part of a collection of galaxies called the Local Group, a gravitationally bound assemblage of more than 50 galaxies, most of them small dwarf galaxies orbiting the two dominant members, the Milky Way and the Andromeda Galaxy. Andromeda, at roughly 2.5 million light-years from our galaxy, is slightly larger than the Milky Way. It contains perhaps 1 trillion stars, compared to our galaxy's 200 to 400 billion stars. The two galaxies are, by cosmic standards, quite close to each other, and they are in fact approaching each other. Gravitational attraction is drawing them together at a velocity of roughly 110 kilometers per second. For decades, the prevailing view was that in approximately 4.5 billion years, they would collide and merge into a single larger elliptical galaxy. But a 2025 study, led by Til Sawala, combining Hubble and Gaia data with 100,000 simulations that included the gravitational effects of the Large Magellanic Cloud and Andromeda's satellite M33, has revised this picture substantially. The chance of a direct collision within the next 10 billion years now stands at roughly 50%, essentially a coin flip, and the chance of a collision within the next 5 billion years is only about 2%. A merger remains possible, perhaps even likely on long enough timescales, but the once confident prediction of a head-on crash has softened into genuine uncertainty. If the two galaxies do eventually merge, the collision will be extraordinarily sparse and gradual because the distances between individual stars are so vast that stellar collisions during the merger will be exceedingly rare. The local group extends across roughly 10 million light-years of space. 10 million light-years, containing more than 50 galaxies. It is, by the standards of what we are about to encounter, a small structure. Beyond the local group lies a larger organizational structure, the Laniakea supercluster, a name given to it by the astronomer R. Brent Tully and his colleagues in 2014 when they published a landmark paper in the journal Nature Redefining the Boundaries of Our Home Supercluster. Laniakea contains the local group, the Virgo supercluster within which our local group resides, the Hydra Centaurus supercluster, and several other previously catalogued superclusters as constituent parts, encompassing roughly 100,000 galaxies. It spans roughly 500 million light-years and contains the mass of approximately 100 million billion suns. Its gravitational center is the Great Attractor, a focal point of mass concentration near the Norma cluster, the point toward which everything in the supercluster is slowly flowing. 500 million light-years. The Milky Way, which felt so incomprehensibly vast when we were inside it, is now a speck within a speck. If Laniakea were reduced to the size of North America, the Milky Way would be smaller than a single grain of sand. But we are not finished, not even close. Laniakea itself is just one of an estimated 10 million superclusters in the observable universe. The universe, at its largest observable scales, is not uniformly filled with matter. It has a structure, a vast three-dimensional web of filaments and sheets of galaxy clusters, separated by enormous voids of near emptiness. This structure, which cosmologists call the cosmic web, is arguably the largest structure known to exist, a scaffolding of dark matter threading through space, with ordinary matter, galaxies, gas, dust, everything we can see, concentrated along the filaments and at the nodes where they intersect. The voids between the filaments are genuinely vast. The Boötes void, a particularly large underdense region of space discovered in 1981 by Robert Kirshner and his collaborators, spans approximately 330 million light-years across. It contains almost no galaxies. It is not a region of interesting emptiness. It is not, as far as we know, filled with anything exotic or unknown. It is simply nearly empty space, a three-dimensional bubble in the cosmic web where the initial conditions of the early universe happened to produce very little density. The Boötes void is so large that if the Milky Way were located at its center, we would not have known of the existence of other galaxies until the 20th century, because the nearest galaxies would have been so far away as to be invisible to all but our most powerful modern instruments. Here is where the textbook answer about the universe's size begins to break down. Or rather, here is where you discover that there are actually several different questions hiding inside the one question you thought you were asking. When someone asks, "How big is the universe?" they might mean any of at least three distinct things. They might mean, how large is the observable universe, the sphere of space from which light has had time to reach us? They might mean, how large is the total universe, the complete extent of space, including the regions we cannot see? Or they might mean something even more expansive. How large is the entirety of existence, including any potential multiverse structures beyond our own spacetime? These are three different questions with three very different answers, and conflating them produces exactly the kind of confused mental picture that most people carry around. The first question, the size of the observable universe, has a well-established answer. The second question, the size of the total universe, has a range of possible answers constrained by observations, but not definitively resolved. The third question remains largely in the realm of theoretical physics and philosophy, not yet anchored by direct measurement. We will work through all three, but to do so, we need to understand the mechanism that created the distinction between them in the first place, and that mechanism is the expansion of space itself. The universe is expanding. This is one of those statements that has been repeated so many times that it has lost its capacity to astonish, and yet it is one of the most profound physical facts ever discovered. When Edwin Hubble examined the spectra of distant galaxies in 1929, building on earlier observations and theoretical work, including that of the Belgian priest and astronomer Georges Lemaitre, who had proposed the expanding universe concept in 1927. He found that the light from distant galaxies was systematically shifted toward the red end of the spectrum. Redshift, in the context of light from distant objects, indicates that the object is moving away from us. And the amount of redshift Hubble observed was proportional to the distance of the galaxy. The farther away the galaxy, the faster it appeared to be receding. This relationship, now called Hubble's law, encodes one of the most counterintuitive facts in all of physics. The galaxies are not moving through space away from us, as though the Milky Way were the center of an explosion. Space itself is expanding. The fabric of space-time is stretching, and galaxies are being carried along with it, like dots on the surface of an inflating balloon. From any galaxy in the universe, every other galaxy appears to be receding, not because there is anything special about any particular location, but because the expansion happens everywhere simultaneously. The implication of this for the size of the observable universe is crucial, and it is the source of one of the most common misunderstandings about cosmic scale. People hear that the universe is 13.8 billion years old and assume the observable universe must therefore be 13.8 billion light-years in radius, since light has been traveling for 13.8 billion years. But this reasoning, intuitive as it is, overlooks the expansion of space. The light reaching us from the most distant galaxies did travel for close to 13.8 billion years. But while that light was traveling, the space through which it moved was itself expanding. The source of that light has been carried far from its original position. The galaxy that emitted the photons now reaching our telescopes is no longer where it was when it emitted them. It has been carried outward by the expansion of space to a position now roughly 46 billion light-years away from us. This is why the observable universe has a radius of approximately 46 billion light-years, not 13.8 billion. The 13.8 billion figure represents the travel time of the light. The 46 billion figure represents the current distance to the sources of the oldest light. Both numbers are correct. They are answers to different questions. The oldest light we can detect, the cosmic microwave background radiation, a faint afterglow of heat left over from the early universe, was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time. Before that moment, the universe was so dense and so hot that light could not travel any significant distance before being absorbed and re-emitted. The universe was opaque. The cosmic microwave background represents the moment the fog lifted, the surface of last scattering, as cosmologists call it. And the photons that have been traveling since that moment form a spherical shell around us in every direction, the most distant thing we can see with any instrument, and the boundary of the observable universe. The cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson, radio astronomers working at Bell Labs in New Jersey. They had built a sensitive horn antenna to study radio emissions from the Milky Way and found an annoying, persistent noise in their signal, a uniform hiss coming equally from every direction in the sky. After ruling out equipment malfunction, pigeon droppings in the antenna, and every other mundane explanation, they concluded that the noise was real and cosmological in origin. What they had stumbled upon, somewhat accidentally without initially understanding what they were hearing, was the echo of the Big Bang itself, the relic radiation of the universe's fiery birth, now cooled to a temperature of approximately 2.7 degrees above absolute zero. Penzias and Wilson received the Nobel Prize in Physics in 1978 for this discovery. The cosmic microwave background has since been mapped in extraordinary detail by a series of space missions. COBE, launched in 1989, WMAPA, launched in 2001, and the Planck satellite, launched in 2009 by the European Space Agency. Planck's measurements, published in a series of landmark papers beginning in 2013 and refined through subsequent releases, provided the most precise picture yet of the tiny temperature fluctuations in the cosmic microwave background, fluctuations that encode, in their pattern, information about the geometry, composition, and age of the universe. It is from Planck's data that our current best estimate of the universe's age, 13.787 billion years, with an uncertainty of roughly 20 million years, is derived. These fluctuations in the cosmic microwave background are not random. They have a characteristic size, a preferred angular scale at which the temperature variations are most pronounced. This scale reflects the acoustic oscillations in the early universe, sound waves essentially, propagating through the hot, dense plasma of the newborn cosmos, their pattern frozen into the microwave background at the moment of last scattering. The characteristic angular size of these fluctuations tells us something profound. It tells us about the geometry of the universe. If space is flat, if parallel lines remain parallel indefinitely, as in standard Euclidean geometry, the fluctuations should appear at a particular angular scale. If space is positively curved, like the surface of a sphere, they should appear larger. If space is negatively curved, like a saddle, they should appear smaller. The Planck measurements indicate that the universe is flat to within a measurement precision of about 0.5%. This is an extraordinary result with an extraordinary implication. A spatially flat universe, combined with the physics of cosmic inflation, the period of extraordinarily rapid expansion in the universe's first fraction of a second, implies that the total universe is vastly larger than the observable portion. How vast? That depends on the details of inflationary models and on exactly how flat the universe really is. Even if the universe's curvature is only at the very edge of what Planck could have detected, curvature so slight that the measurement appears as flat, the total universe would be at least 100 times the diameter of the observable portion. More conservative estimates based on simpler inflationary model suggest the total universe is at least 10 to the power of 23 times larger than what we can see. Some models suggest far more. These numbers are not precise predictions. They are lower bounds, and even the lower bounds exceed any comfortable description of large. But here is what almost nobody tells you about the flatness observation. It does not require the universe to be infinite. It only requires it to be very, very large relative to what we can see. Flatness is a local property, a measurement of curvature within the observable sphere. And a flat local geometry is compatible with a finite universe that is simply too large for its curvature to be detectable at our scale. The universe could be finite and still appear flat to us for the same reason that the surface of the Earth appears flat when you are standing in a field. The curvature is real, but the scale on which it becomes apparent is much larger than the scale on which you are making your observation. Whether the universe is finite or infinite is not a question that current observations can answer definitively. It is one of the genuinely open questions in cosmology. Not a question we have simply not gotten around to measuring, but a question that may be fundamentally inaccessible to measurement, given the constraints imposed by the expansion of space and the finite speed of light. We will return to that inaccessibility, to what it means that there are questions about reality that no conceivable observation can answer, because it is one of the most philosophically significant features of our situation. But before we get there, we need to understand what is actually inside the observable universe, what it contains, how it is organized, and why the structure of what we can see tells us something profound about the structure of what we cannot. The observable universe contains, by current estimates, somewhere between several hundred billion and 2 trillion galaxies, a range that itself reflects an unresolved debate. The upper figure of roughly 2 trillion was published by Christopher Consilis and his colleagues at the University of Nottingham in a 2016 paper in the Astrophysical Journal, and it came from a careful analysis of galaxy number counts at different depths, combined with models of galaxy formation and evolution. A 2021 study using cosmic optical background measurements from the New Horizons spacecraft, taken from beyond the zodiacal light at the edge of the solar system, suggested the total may be substantially lower, closer to several hundred billion. The discrepancy arises because most of the universe's galaxies are too faint and too distant to be directly observed even with the Hubble Space Telescope, and the inferred total depends sensitively on how far the extrapolation is pushed. 1 to 2 trillion galaxies. Each contains on average somewhere between 100 billion and 1 trillion stars. The arithmetic of this is numbing to attempt, but the implication is clear. The observable universe contains more stars than there are grains of sand on all of Earth's beaches and deserts combined. A comparison that sounds like hyperbole, but is, to our best estimates, literally accurate. And every one of those stars is a potential sun. Every one of those suns has the potential to host planets. And every planet around every sun sits within a galaxy that is itself one of a trillion, all of it contained within the portion of space from which light has had time to reach us, which is itself, almost certainly, only a fraction of the total. This is the view from the first layer of the hierarchical structure we are building tonight. The observable universe is the outermost shell we can directly see. Everything beyond it is inference, physics, and in some cases, speculation. But speculation grounded in the best mathematics and cosmological models we have ever produced. And the physics of what lies beyond that boundary is where the story becomes genuinely extraordinary. The boundary of the observable universe is not a wall. There is no edge, no surface, no place where space suddenly stops and something else begins. The boundary is purely a function of time and light speed. It is the distance at which the expansion of space has been carrying matter away from us for long enough that the light from that matter has not yet had time to reach us. Cross that boundary in a hypothetical spaceship. Ignore, for the moment, the physical impossibility of doing so, and you would find yourself in a region of space that looks, in all probability, much like the region you left. Galaxies, stars, planets, the cosmic web of filaments and voids. Just more of what we already know, or perhaps not exactly more of the same. This is where physics becomes genuinely uncertain, and where we need to tread carefully between what is measured, what is inferred, and what is theorized. The leading theoretical framework for understanding the very early universe. The framework that explains the flatness of space, the uniformity of the cosmic microwave background across regions that could not have been in causal contact with each other, and the distribution of structure we observe in the cosmic web, is cosmic inflation. Inflation was first proposed by the physicist Alan Guth in 1981 in a paper that represented one of the most important theoretical advances in cosmology of the 20th century. The core idea is both simple and staggering. In the first fraction of a second after the Big Bang, specifically in an interval so brief that writing the number out requires negative exponents stretching to 30 or more decimal places, the universe underwent a period of exponential expansion, growing by an enormous factor in an extraordinarily small amount of time. The numbers involved in inflation are difficult to hold in the mind simultaneously. The universe, in that initial inflationary period, expanded by a factor that different models place somewhere between 10 to the power of 26 and 10 to the power of much larger numbers, with the precise factor depending on the specific inflationary model and the duration of the inflationary epoch. What matters for our purposes is not the exact factor, but the consequence. Inflation took a region of space that was, before inflation, smaller than a single proton, and expanded it to a size much larger than the currently observable universe. The observable universe, that 93 billion light-year sphere, is, in inflationary cosmology, a tiny patch of an enormously larger inflated region. After inflation ended, the universe continued expanding at a much slower rate, the rate governed by the balance between the gravitational attraction of matter and the repulsive effect of dark energy. But during inflation, the expansion was so rapid that it effectively created an enormous volume of space that is now permanently beyond our observational reach, carried so far away by the expansion that the light from those regions will never reach us regardless of how long we wait. This is worth pausing on. Not the expansion of the observable universe, which is at least accessible in principle, but the fact that inflation almost certainly created a volume of space so large that most of it is causally disconnected from us forever. Not just unobservable right now, due to the finite speed of light and the finite age of the universe, but permanently, irrevocably unobservable, separated from us by an expanding gulf that light will never cross. Estimates of how much larger the inflated universe is than the observable portion vary enormously depending on the model. Some inflationary models predict that the total universe is at least 10 to the power of 23 times the volume of the observable universe. Others, particularly those involving what is called eternal inflation, predict that the inflated region is effectively infinite. Eternal inflation, developed through the work of Alexander Vilenkin in 1983 and Andrei Linde in the same period, is the theoretical scenario in which inflation, rather than ending everywhere simultaneously, ends only in local patches, bubble universes within a larger inflating background. In this picture, inflation continues forever in the background, constantly spawning new bubble universes. In some versions of the theory, particularly when combined with the landscape of solutions arising in string theory, each bubble may settle into a different vacuum state with potentially different physical constants, different particle masses, and different strengths of fundamental forces. Though this further claim depends on theoretical assumptions that go beyond eternal inflation itself. Our observable universe, in this framework, is one bubble among an effectively infinite number of bubbles, each isolated from the others by the eternally inflating space between them. This is the multiverse, not the multiverse of science fiction, which typically involves parallel dimensions or alternate timelines, but the multiverse of inflationary cosmology, an enormous or infinite collection of causally disconnected regions of space, each potentially bearing a different set of physical laws, each a universe in its own right. The multiverse is not a fringe idea. It is taken seriously by a significant number of theoretical physicists and cosmologists, including some of the most eminent researchers in the field. It is also deeply controversial, precisely because it sits at the boundary of what science can in principle test. If each bubble universe is forever causally disconnected from every other, then no observation we can make in our universe can directly confirm the existence of the others. Some researchers argue that this places the multiverse outside the domain of science altogether, a philosophical speculation dressed in mathematical clothing. Others argue that indirect evidence, in the form of the specific values of our universe's physical constants, being consistent with what is predicted by the multiverse framework, constitutes genuine scientific support for the idea. We will hold the multiverse carefully, acknowledging it as a genuine theoretical possibility, without asserting it as an established fact. The honest answer about the multiverse is that we do not know, and more than that, we may never be able to know, which is itself a profoundly significant statement about the limits of what human inquiry can reach. For now, set the multiverse aside and return to something more concrete: the structure of the observable universe itself, and what the James Webb Space Telescope, launched on December 25, 2021, has been revealing about the earliest chapters of cosmic history. The James Webb Space Telescope, built as a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, represents the most powerful astronomical observatory ever deployed. Its primary mirror, composed of 18 gold-coated beryllium hexagonal segments with a combined diameter of 6.5 meters, collects roughly 7 times more light than the Hubble Space Telescope. More importantly, for the purpose of seeing the early universe, Webb observes primarily in the infrared, the wavelengths at which the light from the most distant, most redshifted galaxies actually arrives at our detectors after having its wavelength stretched by the expansion of space. Webb's early observations produced results that surprised even the scientists who built it. Within months of beginning science operations in 2022, Webb had identified galaxy candidates at redshifts, implying distances and ages that challenged existing models of early galaxy formation. Some of these candidate galaxies appeared to be more massive, more mature, and more structured than the models predicted they should be at such early times, suggesting that galaxies formed earlier and more rapidly than had been assumed. The implications of these observations were still being worked through in 2023 and 2024, with some researchers suggesting minor revisions to galaxy formation models, and others exploring more fundamental questions about the physics of the early universe. One discovery generated particular excitement and debate: a galaxy designated JADES-GS-Z 14-0, identified by the JADES collaboration, the JWST, Advanced Deep Extragalactic Survey, and spectroscopically confirmed in 2024 at a redshift of about 14.18, corresponding to a time when the universe was only about 290 million years old. It became the most distant spectroscopically confirmed galaxy on record, and its existence at such an early epoch, luminous, surprisingly mature, and already enriched with oxygen as later observations would reveal, pushed the boundaries of what galaxy formation models had been designed to explain. Subsequent observations have since identified candidates at even higher redshift, including MOM-Z, 14 at Z equals 14.44, suggesting that the era of cosmic dawn was richer with luminous galaxies than early models predicted. Webb has not overturned cosmology. The standard cosmological model, often called lambda-CDM, for the cosmological constant representing dark energy and cold dark matter, remains robust. But Webb has sharpened the questions, refined the timeline, and extended our empirical reach deeper into the universe's first billion years than any instrument before it. What it has not done, what no instrument can do, is see past the cosmic microwave background. That sphere of ancient light, emitted 380,000 years after the Big Bang, is the farthest surface from which photons can reach us. Everything between the Big Bang itself and that moment of last scattering is hidden behind an opaque fog of plasma, a wall of heat and density through which light could not travel. The universe before the cosmic microwave background is, in a very literal sense, invisible to any electromagnetic telescope. But it is not entirely unknowable. There are other messengers. Gravitational waves, ripples in space-time itself, generated by the acceleration of massive objects, are not blocked by the plasma of the early universe in the way that light is. Gravitational waves produced in the first fractions of a second after the Big Bang, by the dynamics of inflation itself, or by phase transitions or the early universe, or by the collision and merger of exotic objects in the first cosmic instance, would pass through everything, including the opaque plasma, and potentially be detectable today. The detection of a stochastic gravitational wave background from the early universe, a diffuse hiss of ancient space-time ripples, would open an entirely new observational window onto the pre-CMB universe. Gravitational wave astronomy began in earnest in 2015, when the LIGO detector in Hanford, Washington, and its partner detector in Livingston, Louisiana, simultaneously detected the gravitational wave signal from the merger of two black holes, a discovery announced in February 2016 that resulted in the Nobel Prize in Physics being awarded in 2017 to Kip Thorne, Barry Barish, and Rainer Weiss. The field has grown rapidly since then, with dozens of gravitational wave events now confirmed, and ambitious future projects, including the space-based LISA detector, planned for launch in the 2030s, designed to extend gravitational wave astronomy to new frequency bands and new source populations. Whether primordial gravitational waves from the inflationary epoch will ever be detected remains an open question. If they are, they will tell us something about the energy scale of inflation, and by extension, about the size of the inflated universe and the nature of what might lie beyond our observable horizon. It is one of the most ambitious scientific goals of the coming decades. Now step back from the instruments and the measurements for a moment. Step back from the numbers and the redshifts and the angular scales of CMB fluctuations. Stand conceptually in the middle of all of this and simply take stock of where the hierarchical map stands. At the center of the map, your body, the atoms in your body, forged in stellar interiors across billions of years of cosmic history, now briefly organized into a structure conscious enough to contemplate its own origins. Immediately around you, Earth, a rocky planet with a radius of about 6,000 kilometers, orbiting a moderately sized star at a distance of 150 million kilometers. Around that, the solar system, a disk of planets, asteroids, comets, and debris extending tens of billions of kilometers from the Sun, enclosed within the heliosphere, the Sun's sphere of magnetic and particle influence. Around that, the interstellar neighborhood, a sparse scattering of stars within a few dozen light-years, each separated from its neighbors by distances of light-years. Around that, the Milky Way, 100,000 light-years across, containing 2 to 400 billion stars, rotating around a supermassive black hole at its center. Around that, the local group, 10 million light-years across, containing more than 50 galaxies bound together by gravity. Around that, the Virgo supercluster, or Laniakea, 500 million light-years across, containing thousands of galaxy groups and clusters. Around that, the observable universe, 93 billion light-years in diameter, containing 1 to 2 trillion galaxies, organized into the cosmic web of filaments, sheets, and voids. And beyond that, the rest of the universe, almost certainly larger than the observable portion, possibly much larger, possibly infinite. Each layer of this map is not merely larger than the one inside it. It is so much larger that the interior layer effectively vanishes, becomes a point, a speck, an abstraction, when viewed from the scale of the outer one. The entire solar system, which felt enormous at our first encounter with it, is invisible at the scale of the Milky Way. The Milky Way, which felt overwhelming, is a point at the scale of the local group. The local group is a point at the scale of Laniakea. Laniakea is a point at the scale of the observable universe. And the observable universe is, possibly, a point at the scale of the whole. This is the hierarchical structure of existence. Not a series of concentric spheres of gradually increasing size, but a sequence of nested containers, each of which so thoroughly dwarfs the one inside it that the interior becomes effectively non-existent from the exterior's perspective. And yet, and this is the reversal that deserves careful attention, the interior does not cease to be real. Your body, at the center of this vast nested structure, is as real as the filaments of the cosmic web. The atoms in your fingernails are as genuinely material as the plasma in the cores of distant quasars. Size is not a measure of significance. Complexity, perhaps, is, and by that measure, the human brain, with its 100 billion neurons and 100 trillion synaptic connections, is one of the most complex structures known to exist anywhere in the observable universe. But we are getting ahead of ourselves philosophically. Before we arrive at that synthesis, we have more layers to examine. Layers that involve not just the structure of the universe, but the composition of what fills it, and the discovery that most of what fills it is something we cannot see, cannot detect directly, and cannot yet fully explain. The universe is not made mostly of the stuff you can see. This is one of those statements that sounds like poetic exaggeration and turns out to be a literal, quantitative, observationally supported fact. The matter you are familiar with, atoms, molecules, the periodic table of elements, everything that makes up stars, planets, gas clouds, and human bodies, constitutes approximately 5% of the total energy content of the observable universe. 5%. The remaining 95% consists of two things: dark matter, which makes up roughly 27%, and dark energy, which makes up the remaining 68%. Dark matter is the older of the two mysteries. Evidence for its existence has been accumulating since the 1930s, when the Swiss astronomer Fritz Zwicky observed that the galaxies in the Coma cluster were moving too fast to be held together by the gravity of the visible matter alone. If the only gravity in the cluster came from the stars and gas that could be seen, the galaxies should have long since flown apart. Something else, something invisible, had to be providing additional gravitational force. Zwicky called it dunkle Materie, dark matter. The evidence for dark matter has since grown overwhelming, coming from multiple independent lines of observation. The rotation curves of individual galaxies, the way stars orbit the galactic center at different distances, are flat rather than declining with distance, as they would be if all the mass were concentrated in the visible matter toward the center. The pattern of fluctuations in the cosmic microwave background matches a universe containing substantial amounts of non-baryonic dark matter. The formation of large-scale structure, the cosmic web of filaments and voids, would not have proceeded as observed without dark matter providing the gravitational scaffolding along which ordinary matter condensed. The astronomer Vera Rubin, working through the 1970s and 1980s with her colleague Kent Ford, produced some of the most compelling and direct evidence for dark matter through systematic measurements of galaxy rotation curves. Rubin's work, which was met initially with skepticism and only gradually recognized as the landmark observational contribution it was, helped establish dark matter as the dominant paradigm in cosmology. She died in 2016, before a Nobel Prize could recognize her contribution, a widely noted gap in the history of science's highest honor. What dark matter actually is remains unknown. It does not emit or absorb electromagnetic radiation at any wavelength. It is dark not just to visible light, but to radio waves, X-rays, gamma rays, and every other form of radiation we can detect. It interacts with ordinary matter primarily through gravity. The leading candidates for its composition include a class of hypothetical particles called WIMPs, weakly interacting massive particles, that would interact with ordinary matter through the weak nuclear force and gravity, but not through electromagnetism. Decades of increasingly sensitive underground experiments designed to detect WIMP interactions have so far returned no confirmed signal, which has led some physicists to explore alternative candidates, including axions, sterile neutrinos, and primordial black holes. There is an alternative to dark matter, a modification of the laws of gravity proposed in 1983 by the Israeli physicist Mordechai Milgram, called MOND, Modified Newtonian Dynamics. MOND proposes that the apparent excess gravitational effects attributed to dark matter are actually the result of a small modification to Newton's law of gravity that becomes relevant at very low accelerations. MOND successfully explains many features of galaxy rotation curves without invoking invisible matter, but it struggles to account for the CMB fluctuation patterns and the large-scale structure of the universe, as well as standard dark matter models do. Most cosmologists consider dark matter the stronger explanation overall, but the debate is not entirely settled, and some researchers continue to develop relativistic extensions of MOND that might address its shortcomings. The honest assessment is that we have abundant, compelling, convergent evidence that dark matter exists, and essentially no direct knowledge of what it is. It fills the halos around galaxies, forms the scaffolding of the cosmic web, and constitutes more than a quarter of the universe's total energy budget. And we cannot say with confidence what particle or particles it is made of. Dark energy is stranger still. Dark energy was not even suspected until 1998, when two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were measuring the distances to Type 1a supernovae in distant galaxies in order to precisely measure the rate at which the expansion of the universe was slowing down. The assumption was that the expansion was slowing. Gravity, after all, should be pulling everything back toward everything else, decelerating the post-Big Bang expansion over time. The question was simply how quickly it was slowing, and what that rate implied about the ultimate fate of the universe. What both teams found, to their considerable surprise and initial disbelief, was that the expansion was not slowing down. It was speeding up. Distant supernovae were dimmer than expected, farther away than they should have been if the expansion were decelerating, which could only be explained if something was actively pushing space apart, overcoming gravity on cosmic scales and driving an accelerating expansion. That something is dark energy. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. Dark energy, in the standard cosmological model, is represented by the cosmological constant, a term first introduced by Albert Einstein in 1917 when he was trying to produce a static universe model, and subsequently abandoned by him when Hubble's observations demonstrated that the universe was expanding. Einstein called the cosmological constant his greatest blunder. It turns out the blunder was abandoning it. The cosmological constant in the current model represents a fixed energy density of empty space, a property of the vacuum itself, which causes space to expand faster as the universe grows larger. The more space there is, the more vacuum energy there is, and the faster the expansion accelerates. This runaway acceleration has an important long-term consequence. Over very long timescales, the expansion of space will carry distant galaxies beyond our observable horizon. Galaxies that are currently observable will, hundreds of billions of years from now, be receding faster than light, not because they are moving through space faster than light, which relativity forbids, but because the expanding space between us and them will be growing faster than light can traverse it. They will redshift to invisibility and eventually cease to be observable, even in principle. The observable universe of the future will be smaller than the observable universe of today, not because the universe itself has shrunk, but because the acceleration of expansion will continuously reduce the volume from which new signals can reach us. In the very far future, trillions of years from now, a civilization in the Milky Way, if any survives, might observe only a small number of nearby galaxies. All the rest will have been carried beyond the cosmological horizon by the acceleration of dark energy. The full richness of the cosmic web, visible to us now, will be invisible to them, not hidden behind clouds or technology limitations, but genuinely gone from any conceivable observation, as surely as the regions beyond our current horizon are gone from us. We are, in a sense, living at a privileged moment in cosmic history, a moment when enough time has passed for the universe to have formed a complex structure, but not so much time has passed that the expansion has erased the evidence of that structure from view. Future astronomers in a dark energy-dominated cosmos will look out and see a much smaller, much emptier universe than we do. They may not have the observational evidence available to us to even infer that the universe was once full of the galaxy filaments and clusters we can now map in such rich detail. This is a melancholy thought, and also a galvanizing one. We are fortunate to exist at a moment when the sky is still full of information. The acceleration of the universe's expansion is directly tied to the eventual fate of everything in it, and that fate deserves a careful examination because the end of the universe is, in some ways, the mirror image of its size, the temporal equivalent of the spatial question we have been asking. Just as the universe is larger than it appears, its future is longer and stranger than intuition suggests. The current phase of the universe's history, the stelliferous era, the age of stars, will last roughly 100 trillion years, or 10 to the power of 14 years. For scale, the current age of the universe is approximately 10 to the power of 10 years. The stelliferous era has barely begun. Stars will continue forming, living and dying for timescales that dwarf the current age of the universe by factors of 10,000. After the stelliferous era ends, when the last low-mass red dwarf stars finally exhaust their hydrogen fuel and cool to dark cinders, the universe will enter the degenerate era, populated by white dwarfs, neutron stars, and black holes. Over incomprehensible timescales, these remnants will themselves decay. White dwarfs may eventually undergo quantum tunneling processes that convert them to iron or cause proton decay over timescales of 10 to the power of 37 years or more, if protons decay at all, which remains experimentally uncertain. Eventually, the universe may approach a state sometimes called heat death or the Big Freeze, a condition of maximum entropy in which all available energy gradients have been exhausted, all organized structures have dissolved, and nothing remains but an extraordinarily dilute gas of particles in an expanding, cooling void. Black holes, the last major organized structures, will evaporate through Hawking radiation over timescales on the order of 10 to the power of 80 to 100 years for the largest ones. After that, an empty, dark, cold, and expanding universe with no structures, no gradients, no processes, and no observers. This is the expected fate of our universe if the current physical laws hold indefinitely, and dark energy behaves as the cosmological constant rather than as some more dynamic field. It is not a certain fate. The nature of dark energy remains one of the deepest open questions in physics, and different behaviors of dark energy lead to dramatically different fates. A big rip, if dark energy's density increases over time, eventually tearing apart galaxies, stars, planets, and ultimately atoms themselves. A big crunch if dark energy somehow reverses, and gravity eventually halts the expansion. Various more exotic possibilities involving false vacuum decay or quantum transitions. We do not know which fate awaits the universe. We do not even know with certainty whether dark energy is truly a constant property of the vacuum or a dynamical field that might evolve over time. This is, again, not a failure of imagination or effort, but a fundamental limitation of the observations currently available. The scale of the universe in time mirrors the scale of the universe in space. Both are far larger, far stranger, and far more uncertain than our everyday experience prepares us to handle. Now we turn to the question of what the size of the universe means. Not just in terms of numbers and distances, but in terms of the physical consequences of living in a universe of this particular scale. Because the size of the universe is not a passive background property, like the color of a wall. It is an active, causal feature that shapes the nature of matter, the emergence of complexity, and the existence of beings capable of asking about it. The universe is as old as it is, 13.8 billion years, because stars need time to form and then explode, and the elements necessary for rocky planets and carbon-based chemistry only exist because generations of stars have lived and died, forging heavy elements in their interiors and scattering them into space through supernova explosions. Carbon, oxygen, nitrogen, iron, the full periodic table beyond hydrogen and helium, all of it is stellar debris. If the universe were much younger, the elements necessary for chemistry would not yet exist. If the universe were much older, the stars necessary to produce those elements might already be gone. The universe is as large as it is, in its observable portion, because of the relationship between its age and the speed of light. A 13.8 billion-year-old universe has an observable radius of roughly 46 billion light-years, not because space was designed to be that size, but because expansion, gravity, and the speed of light produced that horizon given those initial conditions. The size we observe is inseparable from the age we find ourselves in. This connection between age and size, between time and scale, runs through everything we have explored. The universe cannot be understood in space without being understood in time. Its structure is a fossil, a record written in the positions and velocities of galaxies, of the conditions that prevailed in the first fractions of a second after the Big Bang, and the way those conditions evolved across billions of years of gravitational collapse, star formation, and cosmic expansion. Reading that fossil, decoding the size, structure, and history of the universe from the observations available to us is the great enterprise of modern cosmology. It is an enterprise that has produced, within the span of a single human lifetime, a picture of cosmic scale that would have been unrecognizable to astronomers a century ago. And the picture, even now, is almost certainly incomplete. Stand for a moment at the edge of what we know. Picture yourself in a darkened room. Not the room you are actually in, but an imagined one, perfectly dark, perfectly quiet, where the only thing visible is a single point of light directly in front of you. That point of light is everything you have ever seen with your own eyes. The sun, the moon, the stars on a clear night, the planets visible to the naked eye, the faint smudge of the Andromeda galaxy that sharp-eyed observers can detect on the best nights. All of that, every photon that has ever directly struck your retina from beyond Earth, is that single point. Now watch the room brighten, slowly. More points of light appear. Thousands, then millions, then billions. These are the galaxies revealed by telescopes over the past century, from Hubble's photographic plates to the Hubble Space Telescope's deep field images to Webb's infrared portraits of the early universe. The room is now full of light. It seems complete. And then someone opens a door and you see that the room has no walls. This is where we are in the story of cosmic scale. We have mapped the room with extraordinary precision and care. We have counted the lights, measured their distances, traced the architecture of the web they form. And the physics tells us, with reasonable confidence, though not certainty, that the room has no walls. That what we have mapped is a sphere of visibility within an expanse that continues in all directions beyond any horizon we can reach. But the question of how far it continues and whether it continues forever requires us to go deeper into the physics of space itself. Not the contents of space, but space, the fabric, the geometry, the nature of the medium through which all of this light has been traveling. Here is what almost nobody tells you about empty space. It is not empty. The textbook answer is that a vacuum is simply an absence of matter, a region containing nothing. You probably learned this in school or absorbed it from the general cultural understanding of what vacuum means. Space, in this picture, is the passive backdrop against which matter plays out its interactions. A featureless container, inert and without properties of its own. That picture breaks down the moment you look at it carefully. The quantum mechanical description of the vacuum reveals something profoundly different. In quantum field theory, which represents our most precise and complete framework for understanding matter and forces at the subatomic level, the vacuum is not empty. It is a seething, fluctuating sea of quantum fields in their lowest energy state. These fields are not nothing. They carry energy, they fluctuate, and those fluctuations have measurable physical consequences. Pairs of particles and antiparticles spontaneously appear and annihilate, borrowing energy from the vacuum for intervals so brief that the uncertainty principle permits it. This is not a theoretical convenience. It is experimentally confirmed by the Casimir effect, in which two uncharged metal plates placed extremely close together in a vacuum experience a measurable attractive force caused by the suppression of certain quantum fluctuations in the space between them. The Dutch physicist Hendrik Casimir predicted this effect in 1948, and it has been measured with precision sufficient to rule out experimental artifacts. The vacuum has energy, and that vacuum energy, called the zero-point energy, or the energy of empty space, is what dark energy most naturally corresponds to in quantum field theory. Here is where one of the deepest unsolved problems in all of physics emerges. When physicists calculate the expected vacuum energy density from quantum field theory, summing up the contributions of all quantum fields in their ground states, they get a number. When they measure the actual vacuum energy density from cosmological observations of the accelerating expansion, the dark energy density inferred from supernova observations and CMB data, they also get a number. Those two numbers disagree by a factor of approximately 10 to the power of 120 under the standard textbook calculation. Though more refined calculations using different regularization schemes can reduce the gap to roughly 60 orders of magnitude, still by a wide margin the largest discrepancy between theoretical prediction and observational measurement in the history of physics. 10 to the power of 120. This is not a small discrepancy to be tidied up by more careful calculation. It is the largest known discrepancy between a theoretical prediction and an observational measurement in the history of physics. By any reasonable metric, it is an embarrassing disagreement, and it is known in the physics community as the cosmological constant problem. No one knows how to resolve it. Some mechanism, completely unknown to current physics, must be suppressing the vacuum energy by a factor of 10 to the 120, leaving only the tiny residual that we observe as dark energy. What that mechanism is, no one can say. This is one of the most profound admissions available to contemporary physics. We do not understand the vacuum. We do not understand why space has the energy it has, rather than the energy quantum field theory predicts it should have. And since dark energy constitutes 68% of the universe's total energy budget, this means we do not understand the dominant component of the universe's energy content. The universe is mostly something we do not understand, composed of two other things we also do not understand, with only 5%, the ordinary matter, falling within the domain of our well-tested physical theories. This is not a failure of ambition or intelligence. It is the honest ledger of where science currently stands. And standing here at the edge of what is known is not a disheartening place to be. It is a remarkable one. The questions are clearly posed. The measurements are precise. The gaps are identified. Science proceeds not by possessing all the answers, but by refining the precision with which it knows what it does not yet know. Now step back from the vacuum and return to the question of geometry, of the shape of space itself. Because this is where the question of the universe's total size becomes genuinely, irreducibly strange. Space, in general relativity, Einstein's theory of gravity, published in its complete form in 1915, is not a rigid, fixed backdrop. It is a dynamic, flexible geometry that responds to the presence of matter and energy. Mass curves space. The curvature of space determines how objects move. Gravity, in this picture, is not a force transmitted through a mysterious medium, but the geometry of space-time itself. The curvature induced by mass causing nearby objects to follow curved paths. On the scale of solar systems, galaxies and galaxy clusters, this curvature is real and measurable. It is responsible for phenomena like gravitational lensing, where the light from distant objects is bent around intervening massive structures, producing distorted or multiple images of the same background source. Gravitational lensing has become an important cosmological tool used to map the distribution of dark matter, which is itself invisible, but whose gravitational lensing effects on background light can be measured, and to detect distant galaxies, magnified by the gravitational focus of foreground clusters. On the largest scales, the scale of the universe as a whole, the relevant question is not the local curvature produced by specific masses, but the global curvature of the universe as a whole. Is the universe globally flat, positively curved, like the surface of a sphere, or negatively curved, like a saddle. Each of these geometries has different implications for the universe's size and topology. A positively curved universe, a three-dimensional analog of a sphere's surface, is finite in volume. In such a universe, if you could travel in a straight line long enough, you would eventually return to your starting point, just as a traveler on the surface of the Earth, walking always in a straight line, would eventually circumnavigate the globe and arrive back where they started. A flat universe is infinite in the most straightforward interpretation. Flat space extends indefinitely in all directions without boundary. A negatively curved universe is also infinite in the standard interpretation. The Planck measurements indicate a universe that is flat to very high precision. The curvature, if it exists, is smaller than the measurement uncertainty, which translates to a constraint on the universe's radius of curvature of at least tens of times the size of the observable universe. But flatness, as we noted earlier, does not prove infinity. It only proves that the universe is large enough that the curvature, if present, is undetectable to us. There is a further subtlety that is rarely discussed outside of specialist literature. Even a flat universe can be finite if it has a non-trivial topology. Topology is the mathematical field concerned with the global connectivity of spaces, the question of how regions of space are connected to each other, as opposed to geometry, which concerns local properties like curvature. A flat universe could, in principle, be shaped like a three-dimensional torus, the shape you get if you take a cube and connect opposite faces, which would be geometrically flat but finite in volume. In such a universe, light traveling in one direction would eventually wrap around and come back from the other side. You would be able to see the back of your own head, so to speak, if you looked far enough in the right direction. Physicists have searched the cosmic microwave background for the signature of such topological structures, specifically for matched patterns on opposite sides of the sky that would indicate the same region of space being seen from two different directions after light has wrapped around the universe's topology. So far, no such patterns have been found, which places lower limits on the size of any toroidal or other finite topology structure. If the universe has such a topology, its fundamental domain must be at least as large as the observable universe. Otherwise, the matched patterns would be visible. The search continues, and future CMB experiments with higher sensitivity and angular resolution may push these limits further. The deep question of whether the universe is finite or infinite is therefore not settled, and the honest answer is that it may not be settleable by any observation we can imagine making from within the observable portion. This is not the temporary ignorance of science waiting for better instruments. It is potentially a permanent epistemological limit, a boundary between what can and cannot be known, imposed not by the limitations of our technology, but by the fundamental physical fact that information from beyond the cosmological horizon cannot reach us. We cannot know whether the universe is infinite. We may never be able to know. Sit with that for a moment, not as a frustration, but as a genuine feature of reality, a fact about the universe as remarkable in its own way as its enormous size. The universe may be infinite. Infinity is not a poetic exaggeration or a philosophical abstraction. It may be the literal, precise mathematical description of the extent of space. Infinite space, containing infinite matter, producing an infinite number of galaxies, stars, planets, and, by the logic of probability applied to sufficiently large numbers, an infinite number of copies of everything that has ever happened, including this moment, including you, including this exact sequence of thoughts occurring in a mind indistinguishable from yours. This is the implication of a spatially infinite universe combined with the apparent uniformity of physical law across the observable portion. If the same physics applies everywhere and space is infinite, then all configurations of matter that are physically possible will occur, not once, but an infinite number of times. Your exact configuration, every atom in your body in its current position, every memory and expectation in your current neural state, would be replicated an infinite number of times across infinite space, separated by distances so large that the number representing them would require more digits than there are atoms in the observable universe to write. The physicist Max Tegmark, in a 2003 paper in Scientific American, worked through this implication carefully, calculating that your nearest twin, a being identical to you in every physically measurable respect, would be separated from you by a distance on the order of 10 to the power of 10 to the power of 28 meters, if the universe is infinite and uniform. This number is not meaningful in any visceral sense. No experience of distance corresponds to it. But it is not presented as a poetic flourish. It is a straightforward calculation based on the assumption of an infinite uniform universe, and it illustrates how strange the implications of infinity actually are when followed to their logical conclusions. These implications, infinite copies, infinite recurrence, the eternal repetition of all possible configurations, arise from a universe that is simply infinite in spatial extent. They do not require a multiverse in the inflationary sense. They do not require quantum branching or parallel dimensions. They require only that the universe be spatially infinite and governed by laws that apply uniformly throughout. Both of those conditions are consistent with current observations. Neither is proven. This is the landscape of genuine uncertainty at the frontier of cosmology. Not the comfortable uncertainty of a problem that is almost solved, but the profound uncertainty of questions that touch the limits of what physical inquiry can in principle reach. The size of the universe at the deepest level is not a question that can be fully answered with a number and a unit. It is a question that opens onto a horizon of unknowability. And that horizon is itself one of the most interesting facts about the universe we inhabit. Now, having established the full hierarchical structure of cosmic scale, from your body outward to the observable universe and beyond, and having explored the physics of what space actually is and what might lie beyond the horizon, we need to return to something that has been waiting patiently in the background of everything we have discussed. The question of why the universe is the size it is. This is not a question about the mechanism of expansion, which we have covered. It is a question about the initial conditions, about why the universe began with the specific properties that led, over 13.8 billion years, to a universe of this particular scale, with these particular structures in which observers like us are possible at all. The universe we inhabit has several properties that appear, at first examination, to be precisely tuned for the emergence of complexity. The strength of gravity relative to the electromagnetic force, the ratio of matter to antimatter in the early universe, the density of dark energy, the initial density fluctuations that seeded the formation of structure, all of these parameters fall within ranges that, if significantly different, would produce a universe with no galaxies, no stars, no planets, and no chemistry. A universe with significantly stronger gravity would have collapsed back on itself long before stars formed. A universe with significantly weaker gravity would have expanded too fast for matter to clump into galaxies at all. A universe with more dark energy at early times would have expanded so fast that even atoms could not have formed. This observation, that the universe's parameters seem fine-tuned for the existence of complexity, is sometimes called the fine-tuning problem or the anthropic coincidence. It has generated enormous debate among physicists and philosophers with two broad categories of response. The first is the multiverse response. If there are an enormous or infinite number of universes, each with different values of the physical parameters, then it is not surprising that we find ourselves in one where the parameters permit our existence. We could only exist in such a universe, and thus we will only ever observe such a universe, regardless of how rare it might be among all possible universes. This is the anthropic principle applied to a multiverse landscape. It dissolves the apparent fine-tuning by embedding our universe within a larger ensemble in which all possible parameter values are realized somewhere. The second response is to resist the multiverse explanation and seek a deeper physical principle that predicts or explains the observed parameter values from first principles. To find a theory so fundamental that the parameters we observe are the only self-consistent values possible, rather than one random draw from a distribution of possibilities. No such theory currently exists, though string theory and various approaches to quantum gravity have been explored in this direction. Some researchers argue that both responses are unsatisfying. The multiverse response is untestable and therefore arguably unscientific, while the hope for a uniquely determining fundamental theory is speculative in the other direction. The physicist Lee Smolin has proposed a third possibility: cosmological natural selection, an idea developed in the 1990s, in which universes give rise to new universes through black holes, and the physical constants evolve through a selection process analogous to biological natural selection, converging on values that maximize black hole production. This idea makes specific observational predictions, including that our universe should be near the maximum of black hole production for its parameter values, and has been debated extensively in the literature. The honest position is that none of these explanations is established. All of them represent serious scientific and philosophical thinking about a genuine puzzle. The fine-tuning of the universe is a real observation. The universe's parameters do permit complexity in a way that seems non-generic, and any complete theory of physics will eventually need to account for it. This is the kind of question that emerges naturally from asking how big the universe is. The question of size leads to the question of expansion, which leads to the question of inflation, which leads to the question of fine-tuning, which leads to the question of why anything rather than nothing. Each layer of the hierarchy opens onto a deeper layer of inquiry, and the deepest layers are precisely where our current understanding ends and the genuinely unknown begins. What can we say with confidence? The observable universe is approximately 93 billion light-years in diameter. This is a measured quantity, constrained by the cosmic microwave background, the Hubble constant, and the geometry of space. It contains 1 to 2 trillion galaxies, each containing hundreds of billions to trillions of stars, organized into a vast three-dimensional web of filaments and voids. The total universe, the extent of space beyond the observable horizon, is almost certainly larger than the observable portion. The physics of inflation, combined with the measured flatness of space, implies it may be vastly larger, by factors that range from merely enormous to effectively infinite, depending on the inflationary model. Whether the universe is finite or infinite cannot be determined by any observation we can currently make or plausibly imagine making from within the observable sphere. The universe contains, by energy density, approximately 5% ordinary matter, 27% dark matter of unknown composition, and 68% dark energy, whose physical nature remains one of the deepest unsolved problems in physics. The universe began approximately 13.8 billion years ago and will persist, changing in character but not ceasing to exist in any simple sense, for timescales incomparably longer than its current age. And we, the beings asking these questions, looking out through our instruments and our mathematics at the universe that made us, are made of the same material as the stars that preceded us, governed by the same laws that governed the first moments of creation, and constrained by the same horizons that separate the knowable from the permanently unknown. There is something worth pausing on in that last point. The horizon of the observable universe, the boundary beyond which information cannot reach us, is not a barrier imposed on the universe. It is a barrier imposed on us. The universe does not know about our horizon. Matter and energy beyond the horizon continue to exist, to interact, to evolve, entirely indifferent to the fact that their light has not reached us. The horizon is a property of our position and our history, not a feature of space itself. This means that the size of the universe in the deepest sense is not one number. There are at least three numbers: the observable radius, the inflationary radius, and the true spatial extent, which may be infinite. And those three numbers correspond to three fundamentally different questions about what we mean by the universe. The universe we can see, the universe that inflation created, and the universe that is. Disentangling those three concepts is the work of a lifetime, of many lifetimes, of the accumulated effort of thousands of scientists across more than a century of increasingly precise observation and increasingly ambitious theory. And the work is not finished. The map has not been completed. The frontier is still genuinely a frontier. Stop here for a moment and take stock. We have moved outward from the ground beneath you, through the scale of Earth, the solar system, the stellar neighborhood, the Milky Way, the local group, the supercluster, the observable universe. And we have examined the physics underlying each transition. We have met dark matter and dark energy, the two dominant but invisible constituents of the cosmos. We have encountered the cosmic microwave background, the oldest light we can see, and the gravitational waves that might eventually show us what came before it. We have looked at the geometry of space, the topology of the universe, and the profound uncertainty about whether the universe is finite or infinite. What follows from here are the deepest questions, not the questions that science has answered, but the questions that science has sharpened to the point where their difficulty becomes fully visible. Questions about what it means for the universe to have a size at all. Questions about whether size is even the right concept. Questions about what kind of answer to the question, how big is the universe, could possibly satisfy a mind that evolved to navigate a world measured in meters and kilometers, now confronting distances measured in billions of light years and timescales measured in trillions of years. These are the questions that sit at the intersection of physics, mathematics, philosophy, and something older than all three: the simple human impulse to look up and ask what is out there and how far it goes and whether it ever ends. What does it mean for space to be infinite? Not infinite in the poetic sense, not infinite as a synonym for very, very large, but genuinely, mathematically, physically infinite. A space in which every point has an infinite number of other points at greater and greater distances from it, with no outermost point, no boundary, no edge. Our intuitions were not built for this. Every object we have ever encountered has edges. Every room has walls. Every landscape has a horizon. And while the horizon itself recedes as you walk toward it, you understand that this is a perceptual phenomenon, not a physical one. The land has an actual edge. coastlines, mountain ranges, the borders of continents. The Earth has an actual surface. The solar system, while not sharply bounded, has a region beyond which the sun's influence fades to negligibility. All of human experience, all of evolutionary history, all of the cognitive architecture that allows you to navigate the world, all of it was shaped by finite scales, bounded spaces, and edges that could, in principle, be reached. The concept of a truly infinite space is not merely counterintuitive. It may be genuinely unrepresentable in the kind of spatial imagination that human brains generate. And yet, the mathematics of infinity is well defined. Mathematicians have been working with infinite sets, infinite spaces, and the various sizes of infinity for more than a century. Since the work of Georg Cantor in the 1870s and 1880s, who showed that there are different sizes of infinity, that some infinite sets are larger than others, and that the mathematics of the infinite is a coherent and extraordinarily rich field of inquiry. The infinite universe, if it exists, is one in which Cantor's mathematics applies to physical space, in which the number of points in space is not just very large, but uncountably infinite. This is the threshold beyond which numbers fail us entirely. The observable universe contains approximately 10 to the power of 80 atoms. That is a number so large that no human experience provides any grip on it. But it is a finite number, a specific count that could in principle be written down. An infinite universe contains an infinite number of atoms, which is not a very large number. It is not a number at all. It is a different kind of thing entirely, subject to different rules, producing different implications. The shift from finite but enormous to infinite is not a quantitative shift. It is a qualitative one. And it is a shift that the question, how big is the universe, might demand we make, depending on which answer physics eventually converges on. We cannot know right now whether that shift is required. This is one of the epistemological limits that current cosmology has identified with genuine precision. The question of infinite versus finite extent cannot be answered from within a finite observable region. A measurement made from inside the observable universe can only constrain the curvature of space within the observable universe. If the radius of curvature of the universe, the scale on which any positive or negative curvature would become apparent, is larger than the observable radius, then the observable region appears flat regardless of whether the total universe is actually flat, positively curved and finite, or anything else. The measurement cannot distinguish between these possibilities once the scale of curvature exceeds the scale of observation. We are, in this sense, trapped inside our horizon. Not physically trapped. Nothing prevents light or matter from traveling in any direction, but epistemologically trapped. The information necessary to answer the question of the universe's total extent simply cannot reach us, given the physical constraints of how information propagates through an expanding spacetime. This is a remarkable situation. It means that one of the most fundamental questions a thinking being can ask about the universe, how big is it, may have an answer that is permanently, irreversibly inaccessible to any thinking being located anywhere within the observable sphere. The answer exists. It is definite. The universe either is or is not infinite, and if it is finite, it has a specific size. But the information encoding that answer may be separated from us by a gulf that no signal can cross. How do we proceed scientifically in the face of this? How does cosmology continue to make progress on questions that may not be empirically decidable? The answer involves a combination of theoretical constraints, indirect inference, and the development of new observational probes, like primordial gravitational waves that might extend our reach beyond the surface of last scattering. It also involves a willingness to sit with uncertainty, to maintain the map of what is known and what is not known with clarity and honesty, and to resist the temptation to fill the unknown regions with confident speculation dressed as fact. Richard Feynman, the physicist who received the Nobel Prize in Physics in 1965 for his development of quantum electrodynamics, captured this attitude in a phrase that has stayed with me since I first encountered it. I would rather have questions that can't be answered than answers that can't be questioned. The permanently open questions of cosmology, the size of the total universe, the nature of dark matter and dark energy, the physics of inflation, the reality or unreality of the multiverse, are not embarrassing. They are the honest boundary conditions of our current understanding, and they are profoundly interesting boundary conditions to inhabit. Picture yourself standing on a hilltop at night. Not a hilltop on any specific mountain, just a high place, cold and clear, with the wind moving slowly across open ground and the sky above you fully dark. No lights from cities below, no clouds, just the complete, unobstructed dome of the sky, blazing with stars in the way that most people who live near cities have never actually seen. Not the handful of bright stars that punch through urban glow, but the thousands and thousands visible from a truly dark location. The Milky Way as a solid band of light overhead, so dense in places that the dark patches are more striking than the bright ones. Stay there for a moment. Do not calculate. Do not convert anything to light years or parsecs or scientific notation. Simply look up and receive what the sky is offering. What you are seeing in this moment is the light that has survived a journey of varying lengths to reach your eyes simultaneously. The nearest stars, those within a few dozen light years, are showing you light that left them during your own lifetime or your parents' lifetime. Stars at a few hundred light years are showing you light that left them before the Industrial Revolution. Stars at a few thousand light years are showing you light that left during the early Bronze Age, when writing was just being invented in Mesopotamia. The faint band of the Milky Way's densest regions contains light that has been traveling since before the pyramids were conceived. All of that arriving at your eyes at the same moment. The sky is not a flat picture. It is a depth chart, a map of time, every point of light at a different distance and therefore a different era, all of it collapsing into the single instant of your perception. This is the cooling down period, the place in the story where we stop adding new information and simply inhabit the space we have been building. Because understanding the universe's size is not primarily an intellectual achievement, it is an experiential one. The numbers and mechanisms and discoveries are the scaffolding, but what they are scaffolding toward is a particular quality of perception, the ability to look at the sky and feel rather than merely know that what you are seeing is incomprehensibly vast, incomprehensibly old, and still only a fraction of what is actually there. Consider the light you cannot see. Beyond the farthest naked eye star, the telescopes have revealed billions of galaxies, each one a Milky Way, each one containing hundreds of billions of stars. But even the telescopes have a limit. The cosmic microwave background, that faint bath of microwave radiation pervading all of space, marks the boundary of what any electromagnetic telescope can show us. Behind it lies the opaque plasma of the early universe, where the conditions were too extreme for light to travel freely. And beyond the microwave background lies the inflationary epoch. And beyond the inflationary epoch in the theoretical landscape lies the vast inflated region of which our observable universe is a patch, a local neighborhood within a possibly infinite whole. None of that is visible from your hilltop. None of it is visible from any human position, through any instrument we have built or could build. The light from beyond the observable horizon will never reach us. The information encoded in the configurations of matter beyond that boundary is not traveling toward us and will not arrive in any future, however distant. The universe is keeping secrets that it will keep forever. And yet, this is the thing worth sitting with. The universe that we can see, the portion enclosed within our observable horizon, is so rich and so varied and so deeply structured that it took the entire history of human civilization, the accumulated effort of every scientist who ever lived, and instruments of extraordinary sensitivity and precision to begin to map it. The portion we can see took everything we had to understand even partially. The portion we cannot see dwarfs it by factors that resist description. There is something both humbling and strangely comforting in this. Humbling, obviously. The universe cares nothing for the limits of our perception. Comforting, in a quieter way, because it means the universe is inexhaustibly more than we have seen. There is no risk of running out of it. Whatever instruments the future builds, whatever theoretical frameworks the next century develops, the universe will have more to show them than they can absorb. The frontier will not close in our lifetimes, or in the lifetime of our species, or in the lifetime of any species we can imagine arising from the conditions this universe permits. The sky above your hilltop is a door, not a ceiling. It always has been. The recognition of this, the shift from seeing the sky as a bounded dome overhead to understanding it as the visible face of an effectively unlimited depth, is one of the great perceptual revolutions in human history. It happened gradually, across centuries, through the accumulation of observations and the willingness of individual minds to follow the evidence wherever it led, even when it led away from familiar comfort and toward vertiginous scale. Breathe slowly on your hilltop. The cold air moving across the open ground carries with it the same atoms that have been cycling through Earth's atmosphere for billions of years. Atoms that were once inside stars, once inside nebulae, once dispersed across interstellar space, before gravity gathered them into the molecular cloud that eventually collapsed to form our solar system. The air in your lungs is, in a quite literal sense, cosmic debris. You are breathing the remnants of stellar interiors. The iron in your blood was forged in a supernova explosion that predates the formation of Earth by hundreds of millions of years. You are not a visitor to the universe. You are part of it, temporarily organized from its material into a structure complex enough to perceive the whole, or at least the portion of the whole that light has been able to reach. This is not a poetic claim. It is a precise one. Every atom in your body heavier than hydrogen and helium was produced inside a star. Hydrogen and helium themselves were produced in the first 3 minutes after the Big Bang, in the process called Big Bang nucleosynthesis, a period during which the universe was hot and dense enough for nuclear fusion to proceed, producing the primordial abundances of hydrogen, helium, and trace amounts of lithium that still characterize the composition of the universe today. The heavier elements, carbon, oxygen, nitrogen, the elements of biological chemistry, required stellar nucleosynthesis, the sustained fusion reactions in stellar cores that convert lighter elements into heavier ones over millions and billions of years. When a massive star, one substantially heavier than our Sun, exhausts its nuclear fuel, it collapses catastrophically and explodes as a supernova, scattering its processed material into the surrounding space at velocities of tens of thousands of kilometers per second. The material disperses into the interstellar medium, mixes with existing gas and dust, and eventually contributes to the next generation of stars and planets. Our solar system formed from a molecular cloud that was enriched by one or more previous generations of stellar evolution. The calcium in your bones, the oxygen in the air around you, the nitrogen in your proteins, all of it arrived in the solar nebula as the debris of stars that lived and died before our sun ignited. You are the universe's way of looking at itself. This phrase has been used often enough that it risks becoming cliché, but beneath the familiarity lies a genuine and extraordinary fact. The atoms that make up your eyes, your visual cortex, the neural architecture of your perception, all of it emerged from the same cosmic processes that produced the stars those eyes are now observing. The observation is the universe turned back on itself. Matter that began in a featureless hot plasma has organized over billions of years into a structure capable of asking how large the system it arose from actually is. The question, how big is the universe, is, in this sense, the universe asking about itself through us. Stay with that on your hilltop for as long as you need. There is no urgency. The stars will not move perceptibly before morning. The Milky Way will rotate, but on a timescale of hundreds of millions of years. From the perspective of a human lifetime, the sky is essentially static, a frozen snapshot of the galaxy's current configuration. The light reaching you now has been traveling for years, decades, centuries, millennia, and it has waited patiently for your eyes to receive it. Now, from the hilltop, we turn to the deepest question, not the quantitative question of size, but the philosophical question of meaning. What does it mean that the universe is this large? What does it mean for the humans who have spent centuries measuring it? The civilization that has dedicated extraordinary resources to building the instruments of measurement, the individual minds that have absorbed the results and attempted to hold them honestly. Throughout human history, the dominant impulse when confronting evidence of cosmic vastness has been to locate the human within it, to find, in the scale of the universe, some reflection of human significance. The ancient cosmologies placed Earth, and therefore humanity, at the center of everything. The stars and planets were ornaments on celestial spheres, their movements meaningful in human terms, their configurations interpretable as messages addressed to human concerns. The universe, in those cosmologies, was large enough to impress, but not so large as to overwhelm. It was a universe scaled to human importance. The scientific revolution dismantled that comfortable arrangement step by step. Copernicus moved Earth from the center. Galileo revealed the moon as a rocky world, Jupiter as a planet with its own moons, the Milky Way as a collection of individual stars. Newton showed that the same laws governing a falling apple governed the motions of planets around the sun, and, by implication, everything else in the universe. Each step moved humanity further from the center and further from the sense that the universe had been arranged with human significance in mind. The culmination of this process, the full recognition of what modern cosmology has revealed, might seem to leave human beings in a particularly exposed position. Tiny, brief, located on a small rock, orbiting an unremarkable star in the outer regions of one galaxy among a trillion, in a universe that has existed for 13.8 billion years and will continue to exist for trillions of times longer, entirely indifferent to human presence or absence. This is the vertigo that many people feel when they first genuinely absorb the scale of the universe. It is not irrational. The vertigo corresponds to a real feature of reality. We are, by almost any spatial or temporal metric, vanishingly small and extraordinarily brief. The universe does not, as far as anyone can tell, depend on our existence for its continued operation. But here is where the historical parallel becomes instructive, and where the vertigo, if you stay with it long enough, begins to transform into something different. Consider the position of the 15th century European navigators who first sailed out of sight of land into the open Atlantic. The ocean, from their perspective, was featureless and effectively infinite. There was no way, from the deck of a small ship, to know how far it extended or what, if anything, lay on the other side. The scale of the water relative to the scale of the ship was as overwhelming, proportionally, as the scale of the observable universe relative to the scale of a human body. The navigators were tiny, briefly alive, in possession of instruments of limited precision, attempting to orient themselves in an expanse whose boundaries they could not see. And yet, what they did in that situation was not despair. They did not look at the scale of the ocean and conclude that their smallness rendered them irrelevant. They looked at the scale of the ocean and built better instruments. They learned to navigate by the stars, the same stars you are looking at from your hilltop, developing the mathematics of celestial navigation, the craftsmanship of better charts and better compasses, the accumulated wisdom of seamanship across generations. The scale of the problem did not diminish them. It organized them. It gave their intelligence and curiosity a worthy object. The cosmological situation is analogous, with one important addition. The navigators could eventually reach the far shore and stand on new ground. We cannot cross our cosmological horizon. The far shore, if there is one, is permanently out of reach. And this is where the analogy breaks down, not in a discouraging way, but in a way that clarifies what cosmology actually is and what it asks of us. Cosmology asks us to be comfortable with a horizon we cannot cross. It asks us to build the best possible map of what is on this side of the horizon, to measure as precisely as possible, to theorize as carefully as possible, to maintain the map with intellectual honesty, to hold the unknown regions as unknown rather than filling them with convenient fictions. It asks us to find meaning, not in arriving at the far shore, but in the quality of the mapping itself. The Voyager spacecraft, launched in 1977 and now traveling beyond the heliosphere, will never reach another star. It carries a golden record, a physical artifact containing images, music, and sounds of Earth, assembled under the direction of Carl Sagan and his colleagues, on the small chance that it might eventually be found by another intelligence. The chance of this happening is, by any realistic estimate, extraordinarily small. But the golden record was not made because its discovery was expected. It was made because the act of making it, of selecting what to include, of deciding what humanity would want to say about itself to an unknown audience across an unknown distance, was meaningful in itself. The record is an act of attention directed outward, a declaration that we looked and we saw and we cared about what we saw. Every telescope ever built, every spectrum ever measured, every gravitational wave ever detected, every CMB map ever produced, every supernova ever observed, all of it is, in a sense, a golden record. An act of attention directed at a universe that vastly exceeds our capacity to fully comprehend it, made meaningful not by the universe's response, but by the quality of the attention itself. In 1990, the Voyager 1 spacecraft, at the urging of Carl Sagan, turned its camera back toward the inner solar system from a distance of approximately 6 billion kilometers and took a photograph. In that photograph, Earth appears as a tiny point of pale blue light, less than a pixel in size, suspended in the darkness against the scattered sunlight in the camera's optics. Sagan called it the pale blue dot, and the meditation he wrote about that image is one of the most quietly powerful pieces of scientific writing of the 20th century. He wrote about the rivers of blood spilled by conquerors and generals who had imagined themselves the momentary masters of a fraction of a dot. He wrote about the rivers of blood being, from the perspective of that photograph, invisible. Not because they didn't matter, but because the photograph illuminated something about the scale of things that changed permanently, how the scale of things could be understood. The pale blue dot does not say that human lives don't matter. It says that the scale of the universe is so vast that human lives must find their meaning within themselves, rather than from any external feature of the universe. The universe will not tell you that you matter. The universe is not arranged to provide that reassurance. The meaning, if it exists, is something that beings like us, organized from stellar debris, briefly capable of perception and understanding, must generate from within the fact of our own existence. This is not a counsel of despair. It is something closer to liberation. The universe does not owe us significance. We are not owed a cosmos arranged at a human scale, a sky designed to be comprehensible, a history that places us at the meaningful center of everything. We got, instead, something better and stranger, a universe of genuine, incomprehensible vastness, whose laws permit the emergence of beings capable of asking questions about it, whose history is rich enough to be endlessly interesting, and whose unknowns are profound enough to sustain the curiosity of every thinking being this universe ever produces. The scale of the universe is not an obstacle to human meaning. It is the condition that makes human meaning particularly extraordinary. Among 10 to the power of 80 atoms, arranged in the configurations that the physics of this universe permits, the arrangement that constitutes a mind asking how large the containing system is. That arrangement is, by any reasonable accounting, remarkable. Not because the universe is arranged to make it remarkable, but because it is remarkable in itself, independent of any external validation. What does it mean to hold all of this? The 93 billion light-years of the observable universe, the vast inflated region beyond it, the possibly infinite extent of total space, the trillion galaxies, the 100 trillion stars, the dark matter and dark energy that dominate the energy budget and remain largely mysterious. The cosmological constant problem, the question of fine-tuning, the permanent epistemological limit of the horizon. What does it mean to hold all of this while lying in a warm room, letting the day drain away? It means, perhaps, that you are doing something the universe did not know it could do when it began, folding itself back on itself through the medium of a mind and finding that the fold produces something new. Not a comprehensive understanding, that is not available. Not a final answer. The question, how big is the universe, does not terminate in a clean number. But something more interesting than either, a genuine encounter with the limit of what can be known, made from within the thing being measured, using tools assembled from the same material as the thing being measured, sustained by a curiosity that seems to be one of the universe's more improbable outputs. Every civilization that has ever looked up has asked some version of the question we have been exploring tonight. The Babylonian astronomers who mapped the planets across centuries of patient observation. The Greek philosophers who proposed that the stars were distant suns. The Islamic mathematicians of the medieval period who preserved an extended classical astronomy while European institutions were in retreat. The Renaissance astronomers who pointed the first telescopes at the sky. The 20th century cosmologists who discovered the expanding universe, the Big Bang, dark matter, dark energy, and the cosmic microwave background. The engineers and scientists of the 21st century who built Webb and LIGO and Planck and carried human inquiry to the edge of what the physics of information permits. All of them were asking how far it goes. None of them got a final answer. All of them moved the boundary of the known outward by some increment, sometimes a large one, sometimes a small one, and all of them left the horizon intact. The horizon is always there. It will always be there. And the existence of the horizon, the permanent frontier between the known and the unknowable, is not a failure. It is a feature. It is what ensures that the question remains alive, that the curiosity has somewhere to go, that the universe continues to have more to show than any particular moment's best instruments can capture. How big is the universe? Bigger than you can see. Bigger than any instrument will ever show you. Bigger than the number 93 billion light-years, which is already beyond any visceral comprehension. Almost certainly vastly bigger than the observable sphere, by factors that depend on the physics of inflation and range from the merely enormous to the effectively infinite. Possibly infinite in the precise mathematical sense, in which case the word bigger runs out of traction and something more fundamental is required. Not a description of size, but an acknowledgement of boundlessness, and made from one end to the other, from the same material as the curiosity that is asking about it. That is the answer, not the number, which is as close to meaningless as any number can be at these scales, but the relationship. The universe and the question are made of the same stuff. The atoms in the brain asking how large the universe is are the same atoms that the universe used to build itself. The laws governing the neurons that generate the question are the same laws that govern the expansion of space. The time it took the universe to produce a being capable of formulating the question, 13.8 billion years, is written into the question itself, because you could not exist in a Polhawk younger universe, in a universe that had not yet had time to forge the elements and build the stars and allow the planets to cool and let evolution run its long, patient course. The question and the universe are the same age, and somehow, tonight, they are in the same room. The observable universe is approximately 93 billion light-years across. You have heard that number several times now, in several different contexts, and it may have begun to feel familiar. Not comprehensible exactly, but recognizable, the way a word in a foreign language becomes recognizable after enough repetition, even before its full meaning is absorbed. That familiarity is worth examining, because the number has not actually become smaller. The distance has not changed. What has changed is your relationship to it. And that change, small as it may seem, is exactly what this entire journey has been building toward. We began where you are, on the ground, in a body, in a room. We moved outward through the solar system, through the 400 kilometers to the International Space Station, the 384,000 kilometers to the Moon, the 150 million kilometers to the Sun, the 4.5 billion kilometers to Neptune, the vast interstellar distances that reduce Voyager 1, after more than 4 decades of continuous travel, to a position still only a fraction of a light-year from home. We moved through the Milky Way, 100,000 light-years across, containing 2 to 400 billion stars, rotating around the supermassive black hole Sagittarius, a star on a timescale of 225 million years per orbit. We moved through the local group, the Virgo supercluster, the cosmic web of filaments and voids, and arrived at the edge of the observable universe, the surface of last scattering, the the cosmic microwave background, the oldest light available to any telescope we will ever build. And then we looked beyond it, into the inflated region implied by the physics of cosmic inflation, possibly 1,000 times larger than the observable portion, possibly 1,000,000,000,000 times larger, possibly so much larger that the observable universe is to the total universe what a single atom is to Earth, into the question of whether the universe is finite or infinite, a question that current observations cannot answer and may never be able to answer, a permanent epistemological horizon built into the physics of our situation, into the implications of infinity, the endless repetition of all physically possible configurations across an unbounded space, the existence of identical copies of everything in the observable universe separated by distances that make the observable universe look like a dust mote. Every one of these scales was larger than the one before it. Every one of them made the previous scale look trivial, and yet none of them erased the significance of the scale inside them. Not the galaxy, not the solar system, not the planet, not the body from which the looking is being done. The question, how big is the universe, turns out to be a question with at least 3 answers at different levels of resolution. The first answer is empirical and precise. The observable universe is 93 billion light-years in diameter, and this measurement is among the most carefully constrained in all of science, supported by the Planck satellite's measurements of the cosmic microwave background, the Hubble constant determinations from multiple independent probes, and the mathematics of general relativity applied to an expanding space-time. This is the answer science can currently give with confidence. The second answer is theoretical and approximate. The total universe, the inflationary region within which our observable patch is embedded, is almost certainly many orders of magnitude larger than the observable portion, with estimates ranging from conservative lower bounds of 100 times larger to effectively unlimited depending on the inflationary model. This answer is grounded in well-tested physics, but extrapolated beyond the reach of direct observation, and its uncertainty is genuine and acknowledged by the scientists who work on it. The third answer is philosophical and open. The universe may be infinite, in which case its size is not a number, but a property. The property of having no boundary, no largest distance, no outermost point. This answer lives at the frontier between physics and mathematics, and the honest response to it is that we do not know, and the structure of our situation may prevent us from ever knowing with certainty. All 3 answers are true simultaneously at different levels of the question. Holding all 3 together, the precise empirical number, the vast theoretical extrapolation, and the open philosophical possibility, is what it means to understand the universe's size in the fullest sense currently available. The people who have dedicated their lives to building this understanding deserve to be acknowledged, not as a roll call of names and dates, but as a reminder that the knowledge did not arrive from nowhere. It was assembled piece by piece by human beings working with human instruments in human institutions across generations that did not live to see their contributions fully recognized or their questions fully answered. Henrietta Swan Leavitt, who discovered the period luminosity relationship of Cepheid variables in 1908 while working at the Harvard College Observatory as a human computer, a position in which women were employed to analyze photographic plates at wages below those paid to unskilled laborers, gave Edwin Hubble the tool he needed to measure the distance to Andromeda. Her work made the extragalactic universe accessible to measurement, and her name is less widely known than it should be. Arno Penzias and Robert Wilson who stumbled onto the cosmic microwave background in 1965 while trying to calibrate a radio antenna in New Jersey, discovered the oldest light in the universe, the relic radiation of the Big Bang itself, without initially understanding what they had found. They shared the Nobel Prize in Physics in 1978 for a discovery that was, in some ways, an accident organized by careful experimental work. Vera Rubin, who spent decades measuring the rotation curves of galaxies and whose data provided some of the most compelling evidence for dark matter, worked in an era when women astronomers were routinely denied access to major telescopes, and when her results were met with skepticism that her male colleagues' comparable work did not face. She died in 2016, having never received the Nobel Prize that many of her colleagues believed she deserved. Saul Perlmutter, Brian Schmidt, and Adam Rass, who discovered in 1998 that the universe's expansion is accelerating, an observation so unexpected that the teams initially suspected instrumental error, and who received the Nobel Prize in Physics in 2011 for a finding that changed the entire picture of the universe's future and revealed the existence of dark energy, the dominant component of the universe's energy budget. Alan Guth, who proposed cosmic inflation in 1981 and thereby provided the theoretical framework that explains the large-scale homogeneity of the universe, the flatness of space, and the origin of the density fluctuations that seeded all subsequent structure, and who continues to work on the theory, refining and extending it, in the knowledge that direct observational confirmation of inflation remains one of the great outstanding challenges of observational cosmology. And the thousands of researchers whose names do not appear in Nobel Prize announcements, but who calibrated instruments, reduced data, wrote software, built detectors, maintained observatories, and carried out the patient, unglamorous essential work that makes the celebrated discoveries possible. The science of cosmic scale is not the achievement of a handful of geniuses. It is the accumulated labor of an entire civilization, directing its intelligence at the largest available question. That question is not finished. It will not be finished in your lifetime or in the lifetimes of anyone currently alive. The James Webb Space Telescope will continue observing for years, extending our portrait of the early universe's first billion years and refining our understanding of galaxy formation. Future CMB experiments, including CMB-S4, a ground-based telescope array currently in development, and potentially future space missions, will push the measurement of CMB fluctuations to higher precision, constraining the geometry and composition of the universe more tightly than Planck could. The LISA gravitational wave detector, if launched in the 2030s as currently planned, may detect the stochastic background of primordial gravitational waves from the inflationary epoch, providing the first direct observational window onto the physics of inflation and the conditions that set the size of the total universe. Dark matter detectors will continue searching, underground, in space, at particle accelerators, for the particle or particles that constitute the invisible scaffold of the cosmic web. Perhaps they will find it, and the nature of the universe's dominant material component will shift from mystery to established fact. Perhaps they will continue to find nothing, and the theoretical picture will need to be revised. Both outcomes carry information. Both outcomes advance the map. And somewhere in the decades ahead, a student who is perhaps a child right now will encounter some piece of this story, a number, an image, a question posed by a teacher or a book or a video in a darkened room, and feel the particular sensation of the universe opening up beyond what they had imagined. They will carry that sensation into a career in physics or astronomy or mathematics or philosophy, and they will contribute something to the map that we cannot yet anticipate. The frontier will move outward again. The known region will expand by another increment, and the horizon will remain, as it always has, just beyond reach, permanent, serene, and inexhaustibly interesting. The universe does not care that we are asking about it. It does not know that Voyager 1 is crossing the heliosphere, or that the James Webb Space Telescope is photographing galaxies from the universe's first few 100 million years, or that human beings in climate-controlled rooms are lying quietly in the dark and trying to absorb the implications of 93 billion light-years. The universe proceeds with its expansion regardless. Dark energy continues its patient acceleration. Galaxies continue their recession. The cosmic microwave background continues its cooling, currently at 2.725 degrees above absolute zero, dropping by a small fraction of a degree every billion years as the universe expands and the relic radiation redshifts to lower and lower energies. None of this requires our awareness. And yet, our awareness of it is, from the universe's own material and governed by the universe's own laws, one of the things that the universe has produced. The awareness is not outside the system. It is inside it, part of it, a local organization of the universe's matter that has achieved sufficient complexity to model the whole, imperfectly and incompletely, but genuinely. That modeling, this conversation, this long journey outward through nested shells of scale, is itself a cosmic event, a small one by any spatial measure. But scale, as we have seen, is not the only measure of significance. You began this journey lying in a room, looking at a sky you cannot see, asking a question so large that no single answer can contain it. You have traveled, in the space of a few hours, through every layer of the universe accessible to human knowledge and into the uncertain territory beyond. You have met the researchers who built the map and the instruments they used, and the questions those instruments could not answer. You have stood at the edge of what is knowable and looked across the horizon into the permanent unknown. The sky above you, real or imagined, is the same sky it always was. The stars have not moved. The Milky Way has not changed its configuration in the hours since you began. But perhaps the sky looks different now, not because it has changed, but because the depth behind it is more visible to you than it was. Not 93 billion light-years in a single number, but 93 billion light-years as a lived understanding, built up layer by layer through mechanism and history and implication, and the honest acknowledgement of what remains beyond reach. The universe is larger than the universe you can see. It was true in the first sentence, and it is still true now. But now, it means something different. Not a surprising fact, but a foundational one, the ground on which everything else in the story rests. The universe is larger than what we see, by amounts we cannot precisely specify, up to and including infinitely larger. And that vastness is not a problem to be solved, but a condition to be inhabited. A permanent feature of the situation that thinking beings find themselves in, regardless of when or where in the universe they arise. If this changed how you think about the sky, about scale, about the relationship between the questions we ask and the universe that generated the asking, then the time was well spent. Thank you for staying.